First off, we need the balanced equation. So it's methane plus 2 O2s, is that right? These are gases. This is going to produce CO2 plus 2 H2O. So we're just interested in these two here, methane and O2. And they're going to be in a 1:2 ratio. And so we can use, as long as the pressure and the temperature don't change, then we could use the volume ratios here. So 1 liter, 2 liters. And so if I have 15 liters of methane, how many liters? Well, I'm going to need twice as much O2. So for every 1 mole of methane, I need 2 moles of O2. For every 1 liter of methane, I'm going to need 2 liters of O2. As long as the temperature and the pressure are the same. So we don't need to know the temperature and the pressure. We just need to know it doesn't change, and it doesn't change here. And so we need 30 liters of O2. But I'm not asking for the O2, I'm asking for air. And so, so what is it? Well, if we have 21%, this is by mole. But mole is the same thing as a volume percent, which is the same thing as a pressure percent. So this could be 21% mole by mole O2, or it could be 21% by volume O2, or it could be 21% by pressure O2. The first one's always true. The second one is Avogadro's. And the third one is Dalton's. So what we're going to do is we're just going to assume that this is a Avogadro. So for every 21 liters of O2, how many liters of air am I going to have? 100 liters of air. So we'll just do 100 liters of air for every 21 liters of O2. And so the liters of methane cancel, liters of O2 cancel, and that leaves us with liters of air. So this would be the easiest, but there are other ways you could do it as well. You could do it, you convert it to moles and whatnot, or you can assume. You could assume STP, or you could assume room temperature and then calculate it. So 15 times 2 divided by 21 times 100. So 142.8 liters of air, or because we're only allowed 2 sig figs, 140 liters of air. So it's not a number of people got it, but so that should come out too. You need a lot of air because although we only need 30 liters, in 140 liters of air, you're going to have 30 liters of oxygen in there. The rest is mostly nitrogen. All right, any questions on this? All right, we're going to continue with, we're talking about the solutions. So we're looking at solubility. Solubility is going to be affected by the light dissolves light. This first sentence is essentially light dissolves light. We're breaking similar forces and forming similar forces, and they should dissolve. That's for molecules, but we also look at ionic compounds. Look at the rules there. It's going to depend on partial pressure. It's going to depend on temperature. This slide is not fun. So here's light dissolved light. If we mix these two hydrocarbons here, actually these aren't too high. This is water, sorry. If we mix ethylene glycol, which is antifreeze, with water, they're very similar because ethylene glycol, this molecule here, has hydrogen bonding here and hydrogen bonding interactions possible here and here. These can hydrogen with water here, H2O. And so the delta positive of the hydrogen can orient with the delta negative of the oxygen. However, if we mix a hydrocarbon here, like oil and water, they don't mix. So we don't break the hydrogen bonding interactions here, and we don't get the instantaneous dipole interactions here. So those are unlikely. If we look at gases, gases depend on the partial pressure of the gas above the liquid. The higher the pressure, the more you can force the gas particles into the liquid phase. So here. Versus here. That's going to determine the solubility. So the solubility depends on how much pressure there is on the gas above the liquid. Temperature, most things become more soluble as the temperature increases. So what this curve is showing is things becoming more soluble as the temperature increases. There are some things that become less soluble, like lithium sulfate here, but for the most part, the more kinetic energy we have, the more these crystals are going to be broken apart, the solids dissolve. Okay, then those are some notes on solubility, but we're going to look at concentrations. The maximum concentration we could get is called the solubility, but we can have less than the max, and we could have different concentrations. Concentrations is just the composition of the mixture, and so one of these we've already done, percent concentration. The percent concentration by mass is just the mass of solute over the total mass times 100. And so mass of A divided by the total times 100. Well, the total is the mass of the solution. The solution contains all the components, the solute and the solvent. And there could be multiple solutes. So here they show mass of solute over the total mass. In this case, there's only one solute over here. Mass of solvent. We'll do this, some calculations of this. When 125 grams of a solution was evaporated to dryness, 42.3 grams of solute was recovered. What was the percentage concentration of the solution by mass? So, well, the percent concentration is going to be the mass of component A, which would be 42.3 grams of solute over the total mass. The total mass is 125 grams here. There's only one component, the solute. We don't know what that solute is. It could be a mix of salts. But overall, there's 42.3 grams of whatever solutes are dissolved in 125 grams total. So we'll take that, divided by that times 100%, gives us 33.8%. I'd like to keep the symbol here, percent, because sometimes we multiply it by different. Like if we multiply by 100, we get parts per 100. If we multiply by million, we get parts per million. If we multiply by billion, we get parts per billion. So I usually include the units here, 100%. Then if I do a million, I'd call it a million ppm. Billion depends on how concentrated it is. If it's fairly concentrated, we use percent. If it's fairly dilute, we might use part per million or part per billion. It would be the exact same equation, just multiplied by a different factor. Percent composition. Here's how we use percent. You are to prepare 2.50 times 10 squared grams, 250 grams of 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water to use? going to assume that the density of water is 1.00 grams per milliliter. So in this particular problem, why don't you give this one a go? Give this one a go, and then we'll take a break, an early break. I have to do one thing, and then I'll be back.